Hi everyone, this is Dr. Harsa. How are you today? I hope everyone is doing okay. We are just in the second week of the semester. We are already going to start with the first chapter of this course, Signal and System. There are two big parts in this course. Of course, they are signals and systems. Okay, under the topic of signals, we will look at signal classifications and representations that will include signal types, signal models, and some basic signal operation. And then we will look at sampling theory. In this course, we'll be looking at not only continuous signals but also discrete signals. So we are going to look at sampling theory because in this subtopic, you'll be taught how to uh, change or transfer from continuous signals to discrete signals. Before we move to systems, we will look at Fourier series and Fourier transform. We will use Fourier series and Fourier transform to analyze signals, and you'll also look at some Fourier transform applications. In this course, in the system part, we look at linear time invariant systems, yeah, and we're going to see how we're going to analyze these linear time invariant systems in the time and frequency domain. Then you look at impulse response. Impulse response means that we're going to see how linear time invariant system produces output or how it responds to impulse function as the input. Stability criteria will also look into the stability criteria of linear time invariant systems. Okay, for this course, you'll learn Laplace transform. You learn how to apply or use Laplace transform and Z transform as the tools to analyze linear time invariant systems. Okay, for most of these topics that I've mentioned, you're going to learn that in 228, but there are some of the topics that you will only learn in your third year. For signal classification representations, that will be taught in chapters 1, 2, and 3. Chapters 4 and 5, you see linear time invariant systems, and chapter 6 and 7 are the Fourier series and Fourier transform. And lastly, Z transform, you'll see that in chapter 8. And for Laplace transform, you will learn in your third year in EEE228, and for some of you who will be taking EEE254, you will look at Z transform again. Okay, let's start with some basic definitions. What is a signal? Signals are functions. Functions of independent variables that carry information or data. Signals are everywhere. You can't deny that. Simple examples, telephone signals, electric signals, the voltages and currents in circuits are signals, yeah? Acoustic signals like audio or speech signals. And these signals are all functions of independent variable time. Another example would be biological signal. Biological signal is a good example of where it can be either one-dimensional or two-dimensional signals. Signals are functions that exist in many forms. If you look at the examples that I've shown you in the previous slide more carefully, they can be categorized into several types. For example, it can be of continuous functions of real independent variables or real valued functions of discrete variables, or they can also be of discrete functions of discrete variables. And these signals, they can either be in one-dimensional, two-dimensional, or even higher dimension. For example, the speech waveform is an example of a one-dimensional signal, but we may have more than one dimension. The example of the image that in the previous slide, yeah, the medical image, it can be one or two dimension. Okay, so an image, let's say a photograph, is an example of a two-dimensional image. Okay, but if the image is put into motion, as in a movie or video, then we now have a three-dimensional image, where the third independent variable is time. Okay, now what is a system pula? A system is a process. It's as simple as that, yeah. A system is a process. But if you want to put it in a proper words, proper sentence, systems are the entity that process a set of signals to yield another set of signals. There are many types of process. So some simple examples of a process is to extract, to transmit, to improve, to upgrade. Okay, so a system is not limited to physical components, and just because it's a system doesn't mean that it has to be a physical process. Even an algorithm that computes an output from an input is can also be a system. So if we want to summarize what I've just said about signals and systems, so let's look at this diagram. So signals are functions of independent variables. Okay, so a system process the functions, okay, or process the signals, which means that in a system, okay, there's input signals and output signals where the system performs any kind of processing on the input signals to produce output signals. Yeah. Signals represent or encode information. In communication applications, the information is almost always encoded. But in medical equipment, for example, okay, where signals occur naturally, so the information is not purposely encoded. Maksudnya, well, we have the natural signal, but when we use equipment or physical systems to capture those signals, so sometimes the way we represent the signals is like it's being encoded. Yeah. In human speech, we create a waveform as a function of time when we force air across our vocal cords. So there is a natural signal, but the way we capture it, it seems to be like encoded. Okay. Signals such as speech signals are continuous functions of time, but there are also many signals that are discrete functions of time, and there are also other types of independent variables other than time. Okay, these examples of these independent variables like the depth, kedalaman, yeah, temperature, pressure. These can also be independent variables, yeah. But in this course, we will focus only on signals with single independent variable, and the variable is time. Okay, we will only look at one variable and only the variable time. And in this course, we will use this notation, yeah, for continuous time signals, for example, x. So we will use the small x in parentheses. We have t, which represents the independent variable. So the dependent variable is x, the independent variable is t, continuous value time. Yeah. Okay. For discrete signals, so we use the notation small x in square bracket. We have n, where n is discrete value integer. Alright, these are the common notation, but not strictly using t as the to represent time, but usually we use t, and n is the integer value for discrete time signals. Okay, what is it about signal and systems that we will be looking at in this course? We will be doing mathematical modeling. Okay, what are we going to model? we'll be looking at the modeling of physical signals by mathematical functions. We'll look at modeling of physical systems by mathematical equations. We will find the solutions to the equations when excited by the functions. What this means is that we are going to look at what happens to the system. Okay, first we're going to model these systems by using mathematical equations, and then we're going to see what happens to the system when they are being excited by the functions. What happens to the system, or what is the output to the output of the system when we feed the system with inputs. Okay, that's what we're going to do in this course. Not only that, we will look at continuous time and discrete time signals, we will also look at continuous time and discrete time systems. Some examples of these systems are, for the continuous time physical systems, we have electric circuits, op-amps, and pendulum system. And for discrete time physical systems, as the analog to digital converter, picture-in-picture, compact disc, and data acquisition system. Here are some examples. So now let's first look at a linear electric circuit. Does this circuit look familiar? This is RLC circuit, yeah? Okay, this circuit can be represented by this first order differential equation. So if you look at this equation, right, this Vt and It are functions or signals, and this whole equation represents the system. Okay, so the I and the V, It and Vt are the signals, okay, with time as the independent variable, and then the whole equation represents the system. Now, this Newton's law, this is just a physical system. Okay, here also xt is the signal, right? And the whole equation represents the system. Okay. Okay, I want to introduce to you analogous systems. What are analogous systems? If you look at equation A and equation B, equation A is a model of a simple pendulum, and equation B is a model of an LC circuit. If you look here, these two equations, they are of the same mathematical form. For the simple pendulum is a second order differential equation, and for the LC circuit also this is a second order differential equation. So these two systems have the same mathematical form. So these two systems are called analogous systems. By definition, analogous systems are systems that are modeled by equations of the same mathematical form. What does this mean? Okay, this means that if we have systems which are said to be analogous systems, so if we know the characteristics of one system, then we can know, or we can tell what are the characteristics of the other system. Okay. Okay. The next thing that we look at classification of signals, but we will look at that in the next lecture. Yeah, so I will stop here. All right, see you next time.